the recording here has been also started. And we're going to talk about basically stationarity of first-order autoregressive processes. You are going to see it. Okay, so it's visible. And yeah, we're going to continue from lecture 7, which was actually, I will repeat some results here from that. So, but we need to continue. Okay. Now, regarding the representation of first-order autoregressive processes, again, this was from lecture 6 already. Okay, there is a way to represent first-order autoregressive processes as we looked at it. Okay, so this was basically the structure where it started. Keep in mind, guys, epsilon is always a noise. Epsilon t at time point t then. And you have a linear transformation of the past observation at time point t minus 1 for the current observation at time point t. This is what the autoregressive process is. And then, of course, it can be represented that you might see as follows. So this was basically the other structure. Okay, so this is where I would start. And I would consider two cases. The first case where the time is not bounded from below. So you can go back infinitely far. So that was the previous case from the previous lecture. So time basically was identical to the set of integers, negative and positive, whatever. Okay, so you can go back infinitely far. And now we're going to look at case 2, where the time is equal to the set of natural numbers. Okay, so that's going to be basically today's case. If the time is bounded from below, which is, again, so this is the second case. So this is basically case 2, which I was talking about. Again, case 1 was where time was not bounded from below, and that was considered in lecture 7. And the process was stationary if and only if basically the absolute value of A was less than 1. You might remember that. Now, what happens if time is bounded from below? So you need to understand that it is going to look like this. So let's say you have 0, then you have 1, 2, and so on. And that would basically give you the issue that you could not go back infinitely far. So this implies basically that there was a starting value at some point, somewhere. Okay, so there is a starting value basically, and that you could not go back beyond that. Okay, so there was literally meaning that every process has started at some point, somewhere in time, which is, again, more consistent with reality than the other assumption where time was not bounded from below, which was actually a theoretical one. Anyways, so if this is the case, okay, that this means that you could not go back infinitely far. So if you moved ahead at time point t, where time point t is, let's say, the current point of time, you can only go backwards time point t, so t steps basically into the past. Okay, so this is what it would mean, okay, which I did. Okay, so if you're at current time point t, then and n will basically give you the steps how far you go back in time, you realize that the process would yield as follows. So from this structure, actually, we're going to obtain the following. So you need to plug in actually t. So you have v times 1 minus a to the power of t divided by 1 minus a. And then, of course, you have a to the power of t times the starting value. Why the starting value? Because if you set n is equal to t, then t minus n becomes t minus t, and t minus t is obviously 0 then. So that basically would yield or generate the starting value. So this is where basically the process would start. Usually we assume that the starting value is a constant almost surely, which means that at least this is fixed. And again, but this is something that you can have also considered to be random as well. And then you have basically the sum starting at time at point j, which is equal to 0, and then the final summand will be obtained where the summation index j is equal to t minus 1. And again, because you could not go back further, the issue is you have a to the power of j times the noise at time point t minus j. And again, this is basically the last one. So the last noise would be actually at time point 1. There is no noise at time point 0 because at time point 0 there is just a starting value of the process. So you would start from there. Okay, so this is what the structure of the process would look like. Now this is obvious if you look at basically from this perspective, but keep in mind n denotes the number of iterations that you can go backwards in time, and this is the final point. So you could not go beyond that, because if you go beyond time point t or t steps, let's say, then you would have basically a negative time index, which cannot be if time is bounded from below. So this is the other case which I want to look at. Now, as you might guess, okay, if you put the expectation operator on it, the expectation operator will be basically regarding it. So you have a constant here. You have always going to have time dependency of the expectation, no matter what. Okay, so no matter what, you cannot get rid of that time point t or basically time dependency regarding it. So that means that the process is not going to be stationary if time is actually is bounded from below. That's the lesson to learn here, but you're going to see this. Okay, so not now, but I wanted to basically illustrate the point, because in contrast to that, if time is not bounded from below, you can go back infinitely far. Then you can achieve stationarity, if and only if the absolute value of A is less than 1. But I'm going to summarize this. All right, you have the starting value here, and we assume that basically that and this is assumption which we are going to assume without loss of generality. AS means almost surely, and almost surely means probability 1. So that means that the probability that y0 is equal to 0 is going to be equal to 1. I assume this in order to simplify things. So you can basically, put that in much more easier terms. Then this allows me basically to ignore that issue with the starting value. Again, so this is not basically unstraightforward, okay? So that has practical reasons, but if you neglect this assumption, nothing's going to happen. So you don't need to worry about that. Anyways, okay, so I'm going to assume that later on, but not now. So this assumption basically allows me to consider the process a little bit better, or the properties of the process a little bit better, especially when it comes to the covariance and so on. But I will basically mention that after that. So in this case, if time is bounded from below, then the expectation is going to look like this. So as I mentioned before, okay, so if you have that basically, again, so you can simply dismiss that if basically the starting value is equal to 0 with probability 1, but you still have time dependency. So keep in mind, guys, no matter what you're doing, there is always going to be time dependency regarding the expectation of the process if time is bounded from below. This is the lesson that you have to learn here. And if there is time dependency, which means that the expectation, regarding the expectation, so if the expectation depends on time, that this means that the process cannot be stationary. All right, so that's obvious, okay? But this is just based on the structure of time, not inherently structure of the process. Do we understand that, guys? So no matter what you do, you cannot achieve stationarity of the process. The same is true for the variance. So the variance will be also time dependent. Here you have time dependency regarding the variance. So whatever you do, the variance will depend on time. And of course, you can also consider the starting value if you like to. If basically the starting value is equal to 0 almost surely, then the variance of the starting value is going to be 0 as well, because if it's a constant, then it's going to be or having a 0 variance. So you can also, some authors basically drop this from consideration because it feels kind of disturbing, but anyway, you don't need to. This is not what time dependency would come from, so that's why I'm going to basically ignore this term. But anyway, you still have time dependency of the variance, sorry. So you still have time dependency no matter what you do, even if you assume that the starting value is a constant with probability 1. But anyways, okay, so you can get rid of that, so the process cannot be stationary regarding the variance either. And the same is true for the autocovariance as well with respect to the time lag h. If you basically take that, this is going to be a to the power of h times the variance of the process. And I'm going to show that step by step, okay? But keep in mind, guys, the process is not stationary. However, there is a way out, basically. At least you can achieve asymptotic stationarity. Because if you look carefully, guys, if you, let's say, assume that the absolute value of A is less than 1, then this implies that the limit, okay, of the expectation of the process, okay, as basically t converges to infinity, is going to be time independent. So you can see that here because that term will disappear, that will disappear because they will basically converge to 0. Okay, so that means that, since that would converge to 0, if the absolute value of A is less than 1, A to the power of t. Again, so you have a power where the base is going to be basically something between -1 and 1. So it's basically, if its absolute value is strictly less than 1, then a to the power of t will converge to 0 then. Okay, so you need to understand that if the absolute value of a is less than 1, then this thing will converge to 0, and this thing will converge to 0. So then the limit of the expectation will be time independent as t converges to infinity, or it does not converge to infinity because, but let's say as t approaches infinity. Okay, so this is going to be v by 1 minus a, and there is time independency, so the process will be at least asymptotically stationary, but you cannot achieve stationarity fully, but you can achieve asymptotic stationarity. You understand that, guys? Okay, so this is also summarized here, and let me basically, you can say that the same issue we'll have with the variance. So if basically the absolute value of a is less than 1, then this thing will converge to 0, as well as that thing will converge to 0. So then the variance, or the limit of the variance, let's say, the limit of the variance as t approaches infinity is going to be time independent. This is going to be sigma squared by 1 minus a squared. And that's basically time independent. So this expression is time independent. And now for the first time you see a process which is not stationary, but at least asymptotically. All right. If, and that's basically, you need to understand, if this is true, and if it's not true, then you cannot achieve basically independency regarding the limit of these moments. Do you understand that, guys? Okay. So at least we have stationarity in the long run, but we don't have stationarity under this condition, and no matter what you do. And the reason for that is because time is bounded from below. So if time is bounded from below, which unfortunately is more consistent with reality because everything that you observe has started at some point somewhere, let's say based on that assumption, okay, you cannot go back infinitely far. But again, that's how it is. All right. So now if I want to consider, basically, I assume that the starting value is going to be 0 almost surely, which means that with probability 1. If I assume that, then I will collect basically the expectation, the variance, and so on. So you can see that what it's going to be. Now, regarding the expectations, just to confirm that statement, what I was illustrating before, the expectation of that is based on the expectation of a linear transformation, because this is a random variable, and there is basically just a constant. Now, the expectation of a linear transformation, as you might know, is the linear transformation of the expectation. So you can simply take that out from the expectation operator. I'm talking about this constant here, which I'm going to, although basically you have time dependency, it doesn't really matter. If I say it's a constant, I mean, it's not random. All right, so this additive constant basically can be taken out from the expectation operator, and then you have the expectation of a sum. The expectation of a sum is, as you might know, the sum of the expectations. So basically the expectation operator can bypass the sum operator. That's not a big thing. And inside the expectation operator, this time you also have a linear transformation regarding it. So you have the expectation of a linear transformation, which, as I mentioned before, the linear transformation of the expectation. So you can also take out this constant from the expectation operator, as I mentioned before. And the expectation of the noise, as I basically mentioned before, is 0 by definition. So the noise basically has 0 expectation by definition. I mentioned before, a white noise is a stationary process with 0 mean, with a constant variance, and 0 autocovariances if the time lag is not 0. You understand that, guys? So this is basically the case. It's an uncorrelated process. And again, you have that here. So this is basically what it's going to be. You have those zeros. So therefore, this is going to be the expectation of the process. Now check it out, guys. If you take that, and I would consider the limit of that. So you have the limit of the expectation as I mentioned before, as t approaches infinity, you'll find that this is what it's going to be. All right, so the limit, I will just basically collect that again. This is, the limit of this expression. So you have it basically written down like this, 1 minus a to the power of t, and this is going to be divided by 1 minus a. Now the limit is equal to basically v by 1 minus a if, and again I mentioned before, if and only if the absolute value of a is less than 1, because if this is the case, then this expression would converge to 0 as t approaches infinity. Is it clear, guys? Okay, so that's basically a statement here. So, but the lesson to learn here is this: as I mentioned before, you cannot achieve stationarity no matter what you do, but at least you can achieve asymptotic stationarity. All right. So that's something that I would like you to remember. Okay, I'm checking whether this is recording it. Okay, but it does. I apologize. Sometimes it is stopping. Anyways, okay, so I'm going to address the variance. And again, we're going to find the same result. So variance, as far as I can recall, is going to be sigma squared times 1 minus a to the power of 2 times t divided by 1 minus a squared if the starting value is 0. So here, again, I also assume that the starting value, to make things easier, is going to be 0 almost surely. This is an assumption that, you know, kind of simplified things because that's what it's based on. The variance does not depend on additive constants. Okay, so you might remember the variance of a plus x, where x is a random variable, is going to be simply just the variance of x. You might remember this because the variance is measuring distances between the realizations and the expectation. If you increase basically every realization by a, then the expectation will be also increased by a, so the distances between the new realizations and the new expectations will be the same. So variances don't depend on additive constants. So therefore, this is going to be simply just the variance of the sum. Now, the variance of the sum, I saw this basically in the previous assignments, guys, is not the sum of the variances in general. You need to be very careful. Here in this case, it will be because the noises are uncorrelated. If basically the noises are uncorrelated, or any process which is uncorrelated, okay, then you would have to, I mean, you can make it to the variance of the sum is going to be equal to the sum of the variances, but this is just an exception, okay? Some of you guys basically were dismissing that fact from your previous assignment, so you have to penalize it then. But again, in this case, the variance operator can bypass the sum operator, but you need to remember it can only be done if the corresponding summands from which the sum is consisting of are uncorrelated, which they are, okay, because there is no autocorrelation regarding the noise, okay, so therefore no different noises would have actually covariances, so the covariances will be falling out because the variance of a sum is going to be in general the sum of the entries from the variance covariance matrix. So this means you have the sum of the variances plus 2 times the corresponding covariances that are missing. Is that clear, guys? Okay, so this is what I would like you to remind you of. And therefore, okay, in this case now, if you look at the variance of a linear transformation, especially when you have a multiplicative constant, the multiplicative constant can be dragged out from the variance operator, but you would need to square it. So b times x, and you take the variance of that, is going to be b squared times the variance of x. So this thing, if you want to take that out from the variance operator, which you should, needs to be squared. Okay, now what is going to be the square of a to the power of j? If you take the power of a power, then you would need to multiply the exponents. So this is going to be a to the power of j times 2, or 2 times j actually, which I'm going to look at here. And the variance of the noises is going to be sigma squared because the noise is stationary. It doesn't depend on time. It has a constant variance. So you can basically use that one as well. Okay, so that is going to be sigma squared. Now, why do I change that? Because first off, a to the power of 2 times j is equal to going to be a squared to the power of j. Why? Because if you take the power of a power, we're going backwards this time. You need to multiply the exponents, which I did. So that is true. And the reason for that is because this would correspond to a geometric series then. Okay, so you might know what the geometric, or how to calculate basically the geometric series. The formula for geometric series, where q to the power of, let's say, j, where j starts at 0.0 and then you have n, is going to be 1 minus q to the power of n plus 1 divided by 1 minus q. You have probably seen this before. So that's the formula that I'm going to use, because in this case, actually q would resemble to a to the power of 2, okay? So you simply just, replace that, and then, okay, which I did, and n is going to be replaced by t minus 1. So if you replace n by t minus 1, you're going to have this expression, t minus 1 plus 1 in the exponent, that will be yielding t. So you have a to the power of a squared to the power of t divided by 1 minus a squared. That's what it's going to be. So if I adjust basically this formula, which I did. Okay, and then you take out basically sigma squared from the sum, because if you multiply every sum n by sigma squared, that will be sufficient just to multiply the sum by sigma squared, which I'm going to do. Okay, so sigma squared times the sum is going to be the sum, every sum n times the sigma squared, actually. So you have sigma squared times, as I mentioned before, 1 minus a to the power of 2 times t, which I basically, simplified after that. So in the next step, divided by 1 minus a squared, and that is going to be the variance. Now, as you see, okay, so let me basically address this. The limit of that, okay, so this expression is going to approach or going to converge to 0 if basically, the absolute value of a is less than 1 as t converges or t approaches infinity, let's say. So as t approaches infinity, a to the power of 2 times t will be converging to 0. So, and in that case, the variance will be time independent, or the limit of the variance will be time independent, so you can achieve asymptotic stationarity also regarding the time independency of the variance if and only if the absolute value of a is less than 1, because if it's not the case, then that will not converge. Okay, so that's something that you would need to consider. Anyways, I hope this is clear, guys. Okay, so that should be basically clear. And yeah, so regarding the autocovariance, which I'm also going to address here. Okay, so before I address the autocovariance, let me remind you how to basically split the future observations, which I'm going to do. Okay, so the observation at time point t plus h is obtained simply if you look into the formula for the observation at time point t. You'll find that t is here, here, and here, and you simply substitute t for t plus h. So t becomes t plus h, so it does become it here, so does it become here, basically at the upper bound of the sum, and also it's going to be here as well. Okay, so I forgot that one, but I basically tried to mention that. So, you simply substitute t by t plus h. Okay, so as you basically recognize, there is t almost everywhere, let's say, in this expression. But every single time you see it, you would need to substitute it. And now I'm going to split that sum. Okay, and the reason for that is because I want it to compare to this sum. And you will find that there are noises which do overlap and which don't. Okay, keep in mind, guys, there is no autocorrelation regarding the noise, but there is, let's say, the variance if the noises are identical. And I want to check them. Okay, so I want to basically find those noises that are identical. In order to do so, and I did this last time also, I'm going to split that sum. So I'm basically starting at time point j, which, or let's say, at where the index is going to be 0 to h minus 1. So I'm taking the first sums where, the summation index starts by 0, and then it will stop at h minus 1, and then I'm going to continue by h. Okay, so you will basically go on by h. Okay, so from basically j is equal to h to t plus h minus 1. Okay, so again, I was splitting the sum here. Okay, you simply just, you can split it. And now for this sum, you can also substitute j, or basically, which you would actually do. Okay, so you substitute basically the summation index differently, because if you look carefully, guys, the first summand, if j is equal to h, the first summand is going to be t plus h minus h, which is going to be the noise at time point t. So that's going to be, again, let me collect those. If j is equal to h plus 1, you have t plus h minus, in parentheses, h plus 1, which is epsilon at time point t minus 1, and so on. And the last one will be, okay, so if you basically put j to be equal to t plus h minus 1, so basically t plus h will basically dismiss, and that will be the last one. So this is going to be epsilon at time point 1 then, and there is no more. Okay, so these are the noises that are involved from, if you go backwards from 1 to t. Okay, so this is the range where the noises are. Keep that in mind, guys, so you can start counting differently if you like, which I'm going to. So I'm going to modify that sum a little bit. Again, that will stay the same. And if you look carefully, okay, this is going to be the same thing. Okay, so again, keep in mind, these noises are basically considered from epsilon t to epsilon 1 regarding this one, okay, here, this expression. Okay, so these are the noises that are involved if you take the summation index. And what I'm doing here is just simply modifying it. So the first summand is going to be epsilon t regarding the noise. Okay, the second summand is going to be obtained by setting j is equal to 1, which is epsilon t minus 1, and so on. And the last one is going to be epsilon t minus, in parentheses, t minus 1, which is epsilon 1. So these are exactly the same noises as in the previous sum. The only difference is that I basically was restructuring the sum using a different summation index. Simply, you replace j by j plus h. But now you can do that, but if you do that, you need to be careful because you have different limits regarding it. So this starts at time point h, basically, and this would start at basically at j, which is equal to 0. So I'm just basically restructuring the sum. The reason why I'm doing that is because as you might guess, this sum overlaps with that one. The only difference is the constant. And you need to understand that a to the power of j plus h is also equal to a to the power of h times a to the power of j. And since this expression does not depend on the summation index, you can take that out from the sum, which I'm going to do, okay? So that will resemble to the previous one. I mean, I'm talking about this one here, but you're going to see this, okay? So I keep the first one as is, and then I basically take out a to the power of h from the sum. So you have a to the power of h times the same sum as that you would basically find in the previous expression. And these two don't overlap with that one because you have different noises. You understand what I'm saying? So the autocovariance, let's say you can call it the autocovariance, between the green one and the red one is going to be 0 because the noises don't overlap. Keep in mind, guys, regarding the green one, the first noise is at time point t, and the last one is going to be at time point 1. And regarding the red one, which I haven't addressed before, you can see that here, the first noise is at time point t plus h. So this is basically going further. And the last one, if j is equal to h minus 1, this is going to be, and the last one, you can check that out, h minus 1, you put them in here, t plus h, in parentheses, h minus 1, we're going to be yielding a epsilon at time point t plus 1. So as you see, where basically this noise would stop, or basically the red one would stop, the green one hasn't started yet. Okay, so there is always basically, you know, the difference between the two. So the green noises are different from the red ones. So that means that the first sum, I mean, even if you weigh them with some constants, it don't matter. The members of the red sum don't overlap with the members from the green sum. So the autocorrelation will be 0. Okay, and that's what I basically want you to look at. All right, now again, why do you need that? Because I mean, if I want to address the autocovariance, for this expression, I'm taking that. Okay, so simply just copy it. You can see that up here, and I will keep out the additive constants. Again, mentioning before, I simply ignore the additive constants because covariances don't depend on additive constants as well. You can dismiss them. You might remember I was talking about that in a previous lectures. Okay, so when I was, you know, reviewing statistics, covariances don't depend on additive constants. Okay, so this is going to become the covariance of b times x and d times y. You can simply just ignore additive constants. So I was already taking them out. Okay, and that's the reason why I assume that the starting value is not there. So if the starting value is a constant itself, then you could take that also out. I don't want it to basically have that considered either. Okay, that makes things a little bit more, I mean, unnecessarily uncomplicated, which is not true. Again, where all these expressions are coming from, this is basically this expression, okay, that you find here. So simple is, and this expression is here, which can be found here. Again, you can just simply cancel the additive constants, which I did. And as I mentioned before, these two don't overlap in that sense. I mean, don't overlap fully. So if you split that, this is the same as that one, okay? And there is no overlap with this expression, okay? So they don't overlap. So the greens and the reds don't overlap. However, so if this is the case, you might remember the covariance of a sum, or let's say two sums, is simply just going to be the variance if these things are uncorrelated, okay? So if these things are pairwise uncorrelated, the random variables of each world, which they are, okay, then the covariance is going to be degenerating to the variance. So the only thing that matters is the expression that do overlap, because every other expression can be dismissed, which I'm going to do, all right? So this is what I will use, and I did this also in the previous lecture, so again, you can check that out. Here I'm repeating it myself, okay? So these are the noises here from the greens, and these are the noises here from the purple ones, and as you see, they don't overlap with each other. There is a multiplicative constant, so that can be taken out from the covariance, and you're left with basically the covariance of a random variable with itself. Okay, so I was taking that out, and the covariance of the random variable with itself, again, let me remind you, is always going to be its variance, which are basically what I was using here. And I was calculating the variance of the previous expression. The variance of the previous expression, as I mentioned before, was sigma squared, if I recall it correctly, times 1 minus a to the power of 2 times t divided by 1 minus a squared, which was the variance. Okay, so this expression was the variance of the process. So I would simply just basically say, okay, whatever the variance is, multiplied it by a to the power of h to get the autocovariance, and that's it. Okay, so again, the variance of the process is sigma squared times 1 minus a to the power of 2 times t divided by 1 minus a squared. So this is just, you know, a multiplicative constant times a times the variance. So what's true for basically for the variance, which means that it's going to be time independent if the absolute value of a is less than 1. That is going to be also true for the autocovariance as well, guys. So that's something that I want you to remember. All right, now this is kind of interrupted. Anyways, so regarding the first order autoregressive processes, let me summarize basically the two results from the previous lecture as well. This is how it will look like, and if the absolute value of a is less than 1 and time is not bounded from below, so you can go back infinitely far, which we did actually, right? So then the process is stationary. That was the previous result from the previous lecture. Now, however, you could not achieve stationarity if time is bounded from below. So if time is bounded from below, you cannot achieve stationarity, but it's going to be asymptotically stationary if the absolute value is less than 1. And stationarity cannot be achieved. This is not added to these notes, but as I think you could remember that one. All right? However, the issue with time is not very practical one. Time is a metaphysical concept, as I mentioned before. Some people might argue that it doesn't even exist. Again, I will not take sides on that point, so whatever you think about that, this is just, you know, your choice. But again, I don't have time to discuss this. But the issue is, it's not very practical, okay, if you assume that time is not bounded from below. Okay, because what you observe has started at some point somewhere, which might be more consistent with reality. So the issue with that, again, so just to remind you, stationarity is linked to the assumptions of time. Okay, so whatever you assume about time is going to also decide. It's going to also decide or affect basically whether you have a stationary process or not. This is an important issue. Stationarity cannot be achieved if time actually is bounded from below. That's the point. Okay. Time is bounded, you cannot have stationarity, but at least you can have asymptotically stationarity. Okay, so that should be fine. That can be achieved if the absolute value of basically of a is less than 1. However, if you assume that time is not bounded from below, this is not consistent with reality most of the time. Okay, because every process which you observe actually has started at some point somewhere. Okay, so you need to be basically considering that issue. All right, now if basically the process is considered to be stationary in practice, I mean, if I say in practice or from the practical point of view, although these are theoretical considerations, okay, we simply just have if and only if basically the absolute value is less than 1. So strictly speaking, it's not stationary, but basically you can have asymptotic stationarity, so you have stationarity in the long run. So from the practical perspective, it's going to be stationary. Okay, that's what we need to have. Okay, so again, assumptions about time are not very practical in this regard. Okay, so from the practical perspective, all right, so if I say practical, I mean in reality, we're going to have stationarity if and only if the absolute value of a is less than 1. Keep in mind, guys, if I ask you the question whether the process is stationary, okay, you don't need to consider basically the assumptions about time. So you simply say it is going to be stationary if and only if the absolute value of A is less than 1. That's it. Okay? So don't need, I mean, I'm going to give you an assignment where you would have to examine basically stationarity of AR processes. Okay? So if you do this, always do this from the practical perspective. Okay? So I will mention this before, and you need to look at what does that mean basically here from the lecture. All right? Again, I repeat myself, stationarity is achieved for a first-order autoregressive process from the practical perspective, if and only if the absolute value of this parameter is less than 1. Yes, you got a question?
I wanted to ask if we have the data that we are provided with, we can achieve the absolute value of A and lower than 1.
Yeah.
Data, right?
So the issue with that is you need to test that. So there is a hypothesis test involved, which you would consider. And before I answer that question, I need, let's say, 2 to 3 weeks to answer that question properly. But you need to understand there is a difference between stationarity, if you know what the parameter is, but most of the time in practice, nobody knows what the parameter is, so you need to estimate the parameter. Now, if you estimate the parameter, that can be subject to, let's say, to estimation error, whatever. I mean, there is no, I can provide you with basically consistent estimators, okay, but you will always miss it, so you don't going to hit the true parameter value, so always slightly above or slightly below, basically, even if it's basically the estimation is unbiased, you understand? So you need to test stationarity, and there is a hypothesis test involved, and I'm going to teach you how to. That's a different issue. So there is a difference between theoretical consideration, which is, again, if I say practical, I mean which is more consistent with reality, so I need another assumption which is more consistent with reality, but I'm still looking at stationarity from the theoretical perspective. If you want to basically look at stationarity from the empirical one, you would need to perform a hypothesis testing, which I'm going to teach you. So that's.
Can you resolve this issue, because always when you multiply all the data source, one by some constant,
no.
The correlation between them is...
No. You would need to test this at least at the 5% level. So basically the stationarity can be established from the empirical perspective only at the 5% level. So with error probability, which is 5% or less, if it's basically stationary at the 5% level, that is, almost, it is going to be, we're looking at a stationary process in general. That's the issue. Okay, so you need to test this. And I'm going to show you how to. Okay, so there is a little weird hypothesis testing involved, which, again, this is going to throw you off a little bit because the test statistic does not satisfy the central limit theorem if the process is not stationary, which I'm going to address. Okay, so that is the issue which is involved here. And yeah, this is based on the so-called functional central limit theorem. But that goes beyond the scope of this course. I'm going to, let's say, illustrate what this is going to be about, but you need to understand if the process is not stationary, and stationarity is a very important concept in time series, then the corresponding test statistic, which is attached to the slope A, okay, let's call it the slope parameter, is not going to satisfy the central limit theorem. So that's not going to be asymptotically normal. That's the point, and that is a very important issue, okay? So therefore, you need to treat these things a little bit differently as you used to. Okay, but if it's stationary, then it's going to satisfy the central limit theorem. But if it's not, then the test statistic would not converge to the normal distribution, unfortunately. So, but again, in let's say 3 or 4 weeks, I'm probably going to answer that question properly. So I ask you for your patience, okay? I hope you understand. Anyways, okay, so yeah. I'm going to address it, so let's take some examples. So this process, obviously, since basically the absolute value of -2 is less than 1, that means that the process is stationary, as you see. That example, right? And again, if I say stationary, I say stationarity from the practical perspective all the time. Okay, so we're going to ignore the issue with time. All right, so time should not decide whether a process is stationary or not in this case, okay? If it doesn't fit, we make it fit. That's how it works, okay? Again, so the assumptions about time should not basically affect whether a process has a time-dependent mean or not. okay, just because, you know, this is not the case. Anyways, okay, so in this regard, is it understandable, guys? So that's relatively easy to check, at least for first-order processes, okay? So another one, if you take that, that is, of course, I mean, the absolute value of 1.3 is greater than 1, so in this case, the process would not be stationary. There's another example. All right, is it clear? So it basically, when it comes to AR, the first-order AR autoregressive processes, stationarity only depends on the multiplicative constant, and that's it. That's an important result, significant one, but it's a relatively simple one. Okay, so the hypothesis which we are going to look at is just, you know, just to remind you, is going to assume that this is going to be equal to 1. Because if it's equal to, you know, I mean, I will talk about that later on. The null hypothesis is a little bit more complicated, as you might think. Now, the issue with that is this result, my goal is going to be, and I have 45 minutes to address this, is how to generalize that for higher order processes. Okay, so the goal will be how to establish stationarity conditions if you don't have, let's say, a first-order autoregressive process, but let's say a second-order autoregressive process. This is going to be a goal. Now, guys, just to remind you, this is not going to be as easy as you think. Okay, so that is going to be way more, let's say, sophisticated. Again, for first-order autoregressive processes, stationarity only depends on this parameter, actually. That's easy. But second or higher-order processes, that concept cannot be, let's say, generalized in that matter. So we need to have basically two different operators, which I'm going to do, or I'm going to introduce. The first is going to be the difference operator, which you're already familiar with. This is illustrating basically the increments of the process. So you have seen the difference operator, I think. The difference operator is denoted by delta. So this is basically delta, difference operator. And that will basically represent the process at time point. If you look at the difference operator on the process at time point t, this is going to be the process at time point t minus its previous observation at time point t minus 1. So in order to basically to illustrate this, again, there is no multiplication involved. So keep in mind, this is not some sort of a constant times, you know, basically the process, because you have a so-called pseudo multiplication that behaves in such a way that as if you would multiply that, but there is no multiplication involved. So you cannot basically define a constant delta where you would have some sort of a multiplied, I mean, if you multiply that by the process, you would get basically the so-called differences of the process. These are called the increments of the process. Okay, so what you see here are going to be the increments basically of the process. In this case, at the increment, okay, so there is no s involved, at time point t. Okay, but if you collect those, you have basically the increments at time point t. Just to basically to give you an idea how to consider that. So let's say you have a process at time point 1, 2, 3, and 4, and so on. And then you have the observations, let's say, of the process. I mean, at time point 1 is going to be 10, at time point 2 is, let's say, 50, at time point 3 is 30, and at time point 4 is 100. Okay, so let's say these are the observations of the time series, and you want to get the increments of the process at time point t. Now at the first point there is no increment, of course. At the second, 50 minus 10 is going to be 40. Then you have 30 minus 50 is going to be negative 20, and 100 minus 30 is going to be 70. So what you see in red are going to be the increments of the process. Zuwächse in German, that's the term. Okay, so the increments of the process, and that's what you have. Okay, is it clear, guys? All right, so yeah, that's basically what it is. And yeah, so these are the increments, and that's what you will have as written down as a difference operator. Is it clear now? Okay, what you will have? All right, so yeah, and this is just used to represent it. Now, if you apply the difference operator on a constant, this is going to be 0, because again, so the constant would not change, right? So c minus c would be basically equal to 0. There is no time dependency involved, so there is no increment of a constant basically. And if you apply it multiple times, and this is where people confuse this with multiplication, because this is not the way to do it. So you take the increments of the increments, which you can do, increments of the increments, right? Because The increments might be also time dependent of some sort. You have basically that, so you take basically the difference of the increments then, right? Which again you can address. So this issue is called differentiating the process, okay? That's why it's called difference operator. If you want to reverse it, that is going to be the integration of the process. So you can maybe check for yourself if you, let's say, you take those increments of the process and then you sum it up, okay? So let's say with respect to time point 2 and then time point t, if you sum up basically the increments, then you'll have basically the process at time point t minus the process at time point 1. Okay, so that is basically what it's going to be. This is called integration. So you can basically reverse it, okay? How to reverse the integration by differentiation, how to reverse the differentiation by integration. So you can go back and forth, all right? There is no integration operator except for summing it up, okay? But you know, you might know this from integral calculus. So even if you look at continuous time, you know, there is the differences of the process and there is basically the integral which reverses that. So this is basically what it would be, all right? But I'm not going to discuss that here. This is discrete time series, not continuous time series, all right? We need to address discrete time series first, but that's the same principle. Okay, here you differentiated the process twice. So you were taking the increments of the increments. Is this clear, guys? All right, so that's basically how it goes. All right, now, next, we need to also address the so-called lag operator. The lag operator, what it does is it addresses past observations. It doesn't generate them because you need to be very careful. The lag operator is denoted by capital L. Anytime you see capital L in time series, this is most likely to be a lag operator because nobody calls anything like that, you know, so nobody uses the letter capital L for anything, so we basically use that for the lag operator. Now the lag operator is not something that is a mathematical operator that does exist, guys. It doesn't exist because, as you might see, this generates past observation of the process, and that's it. So if you apply it on a process, okay, so you can also write it like this if you like, that will address the past observation of the process, and that is going to be it. But keep in mind, okay, so that's a function actually, this is not a multiplication. So as you might see, okay, there is no such thing as a constant that you could take and then you would multiply it by the current observation of the process to get the past observation of the process. If that was true, the process would be deterministic. You understand what I'm saying? So this operator does not exist in reality because you cannot define a constant in such a way where you would have an observation of the process at time point t that would allow you to generate past observation at time point t minus 1. This is not going to work. Okay, so that's something that you would need to understand. Okay, so this is not going to basically, you know, not going to work here. Is it clear, guys? Okay, so that's some, you need to be very, very careful regarding it. But again, you just basically addressing past observations with that. Now, although this operator does not exist in reality, it's going to be very, very convenient when I try to establish stationarity conditions for higher order processes, just to remind you, okay, this is going to be very important. But I will need to introduce you to it. Okay, so this represents previous observations of the process, okay, at a current point of time. So this is basically just addressing them. If you understand what the difference operator is, then you can also basically get the lag operator as well relatively easily. This is going to be 1 minus a difference operator. If you look carefully, you will going to find that this is going to be true, at least, you know. So I mean that's one can be, I mean, you can simply just say that. Okay, so 1 at t, this is going to be 1 minus delta. That is all applied on that. So this is basically yt and then minus basically the increment. And if you take that out, this is going to yield, okay, so yt minus yt minus 1. And that is going to be yt minus 1. So this is easily confirming that issue. Okay, so you can basically get the lag operator from the difference operator relatively easily. All right, if you apply it on a constant, then this is going to be unaffected. So if you apply the lag operator on a constant, that doesn't affect the constant. So that means that there is no impact basically of the past observation, because there is no past observation regarding a constant. A constant is a constant. It was a constant 100 years ago. So even that basically this is not going to affect it, but you can apply it multiple times. If you apply basically the lag operator multiple times, you basically apply the lag operator on past observations. So you go even further back in time. This is going to be it. So if you want to generalize this, which I might add here to the notes, the lag operator, you can basically say, let's say L to the power of K, applied on a process, would generate basically the observation at time point T minus K. So this is basically how you can address more, several observations from the past. The reason why I'm doing that is because I have just the current observation involved when it comes to the lag operator. Keep in mind, there is no constant that allows you to do it. So this is something that doesn't exist. This is a pseudo multiplication as well as a pseudo exponentiation. But just to remind you guys, I mean, when you look at differentiating functions, okay, so let's say you have fx equals x squared, then you write df by dx, okay, this is going to be 2x. You have also here a pseudo division involved. So this is not a real division. You understand what I'm saying? These are differentials, okay, so you don't divide anything. This is the limit basically of the increments of the function divided by the increments of the argument, okay, as the increments of the argument would converge to 0. This is basically how it's done. So this is a pseudo, okay, division, okay, but it's going to be practical because it behaves as if it was, and that is kind of similar to the lag as well as the difference operator. This is not an exponentiation. This is a pseudo exponentiation, and then you have also basically not a multiplication but a pseudo multiplication, okay? So you can write times if you like, but it's not going to be correct. That's why I don't. Okay, when you basically you consider integrals, you don't have fx times dx. That's not it. So again, there are some people who write it like this. It's not correct because there is no multiplication involved in here. You understand what I'm saying? This is just a pseudo multiplication, okay? But it behaves as such because if you want to do basically to address it, this is going to be the integral of the differential of basically of the function itself. So if you have basically just that, all right? So I mean, you can address it. So the differential of the primitive function like that. That's what it's going to be, all right? But the primitive function again is equal. Sorry, no, the other way around. Okay, so the function itself, fx, is equal to the differential of the primitive function. That's basically what is involved, okay? So this is a pseudo multiplication, okay? All right, so you cannot say, okay, df equals, I mean, you can say df equals fx dx, all right? But it behaves as such. You understand what I'm saying? So we already had things like this without even considering time series. There is no multiplication and division involved, but it behaves as such. So that's why the notation is going to be extremely practical in that sense. All right, guys. So even though it doesn't exist, you understand that concept, guys? I'm not sure. So let's say, have a look at the first order autoregressive process. And I'm going to introduce a different representation for that, and that involves lag polynomials. So lag polynomial is going to be basically a function that involves the lag operator in terms of a polynomial. For example, this is a linear function. Okay, so if you have a linear function where the lag operator is at, then this is going to be a first order polynomial with respect to it, or you can simply say the lag polynomial. Now you can use lag polynomials for representing AR processes. So if you attach the lag polynomial to the process, which I'm going to do, you'll find that this is going to be the constant plus the noise. Now let me explain. You need to break it down, so I'm going to put in the lag operator, the lag polynomial inside, and I'm going to apply it basically on the function. 1 times the current observation of the process is going to be 1 times the current observation of the process, as I mentioned before, and then you have 0.2, let's say, times L times the current observation of the process, but I'm talking about pseudo multiplications. And now you see what the leg operator does. The leg operator basically generates the past observation of the process, but just for representation. And then you can solve this equation for the current observation of the process, and then you'll find that this is exactly the same expression as you have above. So these two representations, that one and that one, are going to be equivalent. Okay, so the only difference between the processes, which you have, first order processes or higher order processes, is going to be the structure of the lag polynomial that is involved. Again, the lag polynomial is a function. You understand what a polynomial is. Polynom, that's a German term, Polynomdivision maybe. So these are the functions that are involved. A parabola is also a polynomial. Any linear function is a polynomial. Cubic functions are polynomials, stuff like that. So where you have basically natural numbers as exponents. If every exponent for the argument is a natural number, then these are going to be polynomials. You understand what I'm saying? So these are the things that are involved. And you can represent any process with respect to a lag polynomial that is an AR process, even higher order processes. And since the lag polynomial is the only thing from which the process would differentiate from each other, except for the concept, but you can simply just ignore that, the characteristics of the lag polynomial will determine what the characteristics of the process are going to be. Okay, so you will need that function, which we're going to address, okay, but you'll see how to. So, but I want you to understand how you would represent AR processes using lag polynomials. I'm going to use another example. So let's say you have a different process, which is, again, that was a previous one. I always took the two. This has a different lag polynomial, as you would see. And if you apply the lag polynomial on the process, okay, which I'm going to do, or you attach the lag polynomial on the process, you're going to get back the constant plus the noise all the time. So for every AR process, this is what it's going to be, and that's what I'm going to address. You see this over here. 1 times the current observation of the process is 1 times the current observation of the process, literally speaking, and minus 1.3 LYT becomes 1.3. You have the lag operator involved. The lag operator generates past observations, so you have the current observation minus 1.3 times the past observation of the process. And if you solve this basically for YT, you'll find that this expression is equal to the process itself. So here you get it back. So that means that this representation where the lag polynomial is involved is equivalent to that. You understand what I'm saying? So all I need to do is to specify the so-called lag polynomial of an AR process, because every AR process has a lag polynomial. Okay, you're going to see higher order ones also. And the characteristics of the lag polynomial, basically the characteristics of the process, including stationarity, will be determined by the lag polynomial, by the characteristics of the lag polynomial. So I'm going to express basically stationarity conditions based on characteristics of the lag polynomial. This is actually what I'm going to do. And tomorrow we're going to discuss it a little bit further. So don't be afraid. It's going to be very simple. Now, regarding the roots of the lag polynomial, because how do I identify stationarity? When it comes to first-order autoregressive processes, that was very easy. So when it comes to stationarity of first-order autoregressive processes, this process was stationary because this parameter had an absolute value which is strictly less than 1. So as long as this is the case, the process is going to be basically stationary. All right? Now, but you can address it right there, right? That's going to be true. Now, regarding the lag polynomial, I'm going to discuss the properties of the lag polynomial of a stationary process. You need to understand that. Now I'm going to look at the roots of the lag polynomial. The term roots is confusing for German-speaking people. It means Nullstelle. I don't know if you heard that term Nullstelle, okay? So the roots has a double meaning. One is the square root or, the cubic root, wherever. And the other one is, for German-speaking people, Nullstelle. You understand what I'm saying? So some people don't know this. You need to calculate the Nullstelle of the lag polynomial, okay? You understand what I'm saying? So that's called the root, so don't confuse the two, guys. All right? That's what I'm going to do. What is the, let's say z is a root, okay, of the lag polynomial, so that means that if you put that into the lag polynomial, you're going to get 0, and I need to find those. So this is relatively easy, guys. 1 plus 0.2 times z is going to be 0 if z is a root, and if you solve this for z, you're going to get -5. Now, the lesson to learn here is this. if the process is stationary, then the roots of the Lac polynomial will have absolute values that are greater than 1. You refer to that, that means that the roots are outside of the so-called unit circle. The unit circle is basically that, you understand? So unit circle, you know, I mean, it can be complex. So you have a real part, and then you have an imaginary part regarding the roots, because polynomials can have complex roots as well. Think about quadratic equations. There is a unit circle, all right, so this is here. There is a unit circle, you know, and then if you're outside of the unit circle, so if every root is outside of the unit circle, then the process is going to be stationary. That's the lesson to learn, all right? So the absolute values, okay, that's what it's called, unit circle, okay? If the absolute values of all roots are going to be greater than 1 if the process is stationary, and that is also true the other way around, okay? If the process is stationary, then the roots, okay, then the roots are going to have absolute values that are greater than 1. And the other way around, if the roots have absolute values that are greater than 1, then the process is going to be stationary. To see this, I'm going to use the other example for which the process was not stationary. So keep in mind, guys, this process was not stationary because the parameter 1.3 has an absolute value which is greater than 1. Now, as you will see, the root of the Lac polynomial will have basically a root which is less than 1. Okay? So that's inside the unit circle, if you say. You understand what I'm saying? So in this case, this is what it's going to be. So you can examine stationarity regarding roots of the Lac polynomial. And if every root has an absolute value which is greater than 1, then the process is going to be stationary. And if there is one single root which has an absolute value that is less than 1, the process is not going to be stationary. Point blank period. This is what the generalization is going to look like. Again, check this out. Okay, so if you solve this for z, which is the root, you're going to get 10 by 13. As you see, 10 by 13 is less than 1, and of course the absolute value of that also. This means that the absolute value, since the absolute value basically of the root is less than 1, the process is not going to be stationary. You understand what I'm saying? This is going to be the generalization. Now, let me basically recall this. In general terms, this is how it's going to be, okay? There is another aspect for which I'm going to address. If the process is stationary, the lesson to learn here is this, then the inverse of the Lac polynomial will be finite. This is going to be a little bit more abstract concept. Okay, so what does that mean, inverse of the Lac polynomial? I want you to remind you that you can basically use different representations. Okay, so I'm going to use that one. You can see it over here, and I'm going to discuss it. So that's going to be in another representation. Okay, and as you see, okay, check it out, guys. If this expression exists, then you just have a linear transformation of the noise. And if you have a linear transformation of the noise, you understand what I'm saying? The noise is stationary, so the linear transformation of the noise is also going to be stationary. You understand what I'm saying? So the process is going to be stationary then. Simple is. Now, why is that equal to that? So the only thing that basically is required is that to exist. Okay? Does it exist? Yes or no? Okay? Does it exist? Yes or no? Okay? That's a question that you would need to ask. If it exists, then, as you see, the process is a linear transformation of a noise, to put it in simple terms. Why? Because, again, you might remember if you attach the Lac polynomial to the process, you're going to get the constant plus the noise. You understand? So, if you might solve this for, basically for the process, which you can do, okay? So, you can do it in a second step, okay? So, yt equals, and then what? You would have basically v divided by the inverse of the, divided by the Lac polynomial, let's say, which is the multiplied by the inverse, and then you have the noise divided by the Lac polynomial, okay? And I was writing it like this, okay? So that is a more straightforward notation, because in this case you see that if this exists, if this expression exists, which means that this must be finite, then the process itself is just a linear transformation of the noise. All right? But that involves also past observation of the noise. Understand that, guys. This is an issue. And since the noise is stationary, any linear transformation of the noise is going to be stationary. You understand that? So the statement that I'm going to make, and that's going to be the second statement, I'm going to discuss that tomorrow a little bit further. If the inverse of the lag polynomial exists, then the process is stationary. If the process is stationary, then the inverse of the lag polynomial must exist, because otherwise you could not get stationarity. You understand what I'm saying? But that is a little bit more, let's say, more sophisticated approach, other than the checking the roots of the lag polynomial. So I give you one assignment, basically you would need to address what the inverse of the lag polynomial is. Let me discuss this a little bit further. Okay, so you'll see in this case, this is how the lag polynomial looked like. You understand? In this case, because this is how it is here. Okay, and now when does that exist? Okay, you might remember that 1 by 1 minus q equals basically the geometric series, all right? So this is the limit of the geometric series. Sorry, it starts at 0.0. But when does it exist? It exists if, okay, so that exists if basically the absolute values of q is less than 1. So the geometric series converges if basically the base has an absolute value which is less than 1. You understand what I'm saying? So in this regard, this thing would exist if and only if, similarly, this is going to be finite because that will converge if and only if the absolute value of A is less than 1, similar to the convergence of a geometric series, guys, in this case. You understand what I'm saying? So this is how you would address that issue, all right? But I'm going to discuss this a little bit further because, again, so this is not, again, here you see, right? That's the condition, okay? And this is basically applied on A, all right? So that means that this exists, right? Which I'm going to address it here. As you see, this is the lag operator applied on a constant. Now, if you apply the lag operator on a constant, that will be the constant itself. So you can simply dismiss the lag operator. Okay, and that will mean that if you go backwards, and this is what I'm going to do, if you go backwards, which I address, okay, that will be 1 by the lag polynomial at point 1. How come? Again, if you apply the lag operator on a constant, keep in mind v is a constant, then the lag operator disappears because the constant has no past. You understand what I'm saying? And therefore, this expression is going to be 1 by 1 minus a. So 1 by 1 minus a is also 1 by 1 minus a times 1. So this is actually what you see 1 by the lag polynomial at point 1. All right, so this is basically just a simplification times a constant, and then you have the other expression which you're left with. So you don't need to take care of that anymore. That's going to be the same for every autoregressive process, but you might need to take care of that. You need to check, and this is what it's going to be, when does this expression exist? Okay, so when does it exist? Okay, so that's the question that you would need to ask. Because if this thing is finite, then the process is going to be stationary, okay? Because then it's just a simple linear transformation of these noises. You understand what I'm saying? So again, but provided it does exist, because if it's not, then it's not going to be. And it exists, and let me just rephrase that, if and only if, and that's a lesson that you would need to learn, the absolute value of A is less than 1. How come? Because of the convergence of the geometric series. This series does not converge if Q has an absolute value which is greater than or equal to 1. That's the condition that I want to establish. Now, how would you do this for a higher order processes using Taylor series? I'm going to teach you that tomorrow. So when it comes to higher order processes, how would you basically find the inverse of lag polynomials? The inverse of lag polynomials will be found by applying the Taylor series. Okay, so that's going to be another issue. But I'm not going to do it now. Okay, so I'm going to summarize these things. The process, again, just keep in mind, guys, this is a representation. In this case, just simply giving you the lag polynomial. If you apply, or basically if you attach it to the process, you're going to get back the constant plus the noise. Every AR process there is, even for higher order processes, you're going to see this. And the process is stationary. So let me basically summarize that. If and only if the first condition that you learned last week was that the absolute value is less than 1 and time is not bounded from below. You understand what I'm saying? But I'm keeping that out of consideration. So I'm not going to basically discuss the issue with time anymore because this is not a practical one. Okay, this course is also maybe rather a theoretical than a practical one, but I need to basically address what is going to be in practice as well. Now, the other thing that I found is this. Again, so these are things that you had heard before, okay? And again, ignore the issue with time. I'm not going to talk about time anymore, okay? The other thing that you would need to consider is the process is stationary if and only if, and that was basically the second condition that I mentioned, if and only if the roots of the Lac polynomial have absolute values that are greater than 0 without any exception. Not a single root has an absolute value which is less than 1. Understand what I'm saying? So this is what it's going to be, all of them. If I say all of them, I mean all of them, okay? Wenn ich sage alle, dann meine ich alle, you understand? So this is what it is. Average, I mean, in a case of first-order autoregressive process, there is just one root. So linear function can only have one, okay? But in a second-order process, it can have two. You understand what I'm saying? For a third-order autoregressive process, that can be 3, and so on and so on, okay? So every single one of them needs to have an absolute value which is greater than 1. We saw this when it comes to the first-order autoregressive process, okay? So I'm going to write that statement down. If z is a root, that this implies that the absolute value of z is greater than 1. You understand? And keep in mind, guys, and this is going to be very important, so when it comes to higher-order processes, z can be a complex number also. So every second-order autoregressive model will have 2 roots. You understand what I'm saying? Or maybe 1, but 2. Okay, there is, if the discriminant is negative. You understand what I'm saying? So when it comes to a quadratic equation, you know what a discriminant is, you know? So yeah, and if the discriminant is negative, there is also 2 roots. Discriminant, you know the formula, x squared, a times x squared plus b times x plus c equals 0. This is x12 is equal to minus b plus minus the square root of b squared minus 4 times, sorry, I don't have space. I'm going to rewrite it again. So x equals minus b plus minus the square root of b squared minus 4 times a times c divided by 2 times a. You understand that, guys? So what you find under the square root is called the discriminant. You understand what I'm saying? If the discriminant is positive, you have 2 real roots, you know, and if the discriminant is negative, then you have 2 imaginary roots. Okay, so keep in mind, because the roots in this case, okay, so z can be a complex number. Okay, the complex number, you know that structure, right? A plus b times I, where I is the square root of -1. I'm going to address it tomorrow, so don't need to take care of that. All right? Now, again, that was basically the second condition, and now there is a third. If the inverse of the Lac polynomial is finite, okay, which means that this sum would exist. Keep in mind, guys, so this is basically must be finite. These alphas, okay, when it comes to the first order autoregressive process, alpha 0, that coefficient is equal to 1. Alpha 1 is going to be equal to a, alpha 2 is going to be a squared, alpha 3, okay, so these are the alphas, sorry. Okay, these are going to be some coefficients. And when it comes to the first order autoregressive process, this is how these coefficients are going to look like. If you have a second order autoregressive process, then these coefficients might change. You understand? So these coefficients, these alphas, okay, so these are the ones that I'm talking about that you see here, okay, can be different for higher order processes. But when it comes to the first order processes, this is how it's going to look like. I'm going to discuss it tomorrow, so if you don't understand this, don't worry. Okay, but you would need to establish these coefficients because that might look different. Okay, so this is a general expression when it comes to the inverse of the Lac polynomial. Every inverse is going to look the same. I mean, it's not going to look the same, but it will have the same structure. The only difference is going to be that there is different coefficients, but that's that. Okay, so I'm going to address that tomorrow, don't worry. Okay, now, before I leave you, I'm going to tell you how to address this issue for higher order autoregressive processes. And as you see, this condition, these two will stay. They don't change. Okay, so what is true in this regard for first order autoregressive process, or what was true, is going to be also true for higher order processes. Okay, so the first one, or actually the second one is, let's say, a little bit more practical. The process is going to be stationary if and only if, and this is how it will look like, so check it out. The only difference is that the lag polynomial will going to look different. But that's it. So this structure will be the same. Okay, only the lag polynomial will look different. You understand? So I keep this structure, right? And if you solve this for yt, this is going to be v by a at point 1 plus the inverse of the lag polynomial times the noise. That's it. Okay, so what you need to look at actually is how the inverse of the lag polynomial would look like, and this is going to be the structure. It must be finite. If it's finite, the process is going to be stationary. It's actually, this is meaningful, guys, okay? Although it might be a little bit difficult to address the inverse of the lag polynomial, so how to find that, I'm going to teach you that too. You use the so-called Taylor expansion, okay? But that's something that I want to skip now, at least, okay? So this is what I'm going to look at. If all roots of the lag polynomial have absolute values that are greater than 0, and keep in mind, guys, that the roots can be complex. Now, let's say if z is a complex number, which is looking like this, so a plus b times the square root of -1, then the absolute value of z, I'm going to use the Euclidean norm, if you allow me to do it, because there is different norms regarding, complex number is a vector, okay, so you can have different vector norms, but I'm going to use the Euclidean one. This is the easiest one, okay? This is going to be the square root of, let's say, of a squared plus b squared, okay? So this is what it's going to be, and that's it, okay? So this is how you calculate the absolute value of a complex number, but I'm going to give you examples based on that one, so don't worry. We're going to simply use the Euclidean norm. Anyway, all right? So, but that's that. So the most important one is going to be that, okay? So the process is stationary if and only if all roots of the lag polynomial we're going to have absolute values that are greater than 1, and that's what I'm going to discuss tomorrow. And after that, I'm going to, maybe I'll discuss that one first when it comes to basically how to find these coefficients, because you need to find these coefficients, okay, to get the inverse of the lag polynomial. When it comes to the first order autoregressive process, that was easy, because 1 by 1 minus a was equal to the limit of this sum where you have a to the power of j, right? So that's it. So if you take basically these, a to the power of j, this is resembling to these coefficients, okay? And that's what it was, okay? And you can also get the lag operator back, but you don't really need them. All right, that's it. So this is how it would look like, and I'm going to discuss, in this case, the geometric series would be fine. You don't need the Taylor expansion because you know that limit. Okay, so nobody basically needs a Taylor expansion to find a coefficient for a first order autoregressive processes, but you would need the Taylor expansion for higher order autoregressive processes. I'm going to teach you how to do it for the first order autoregressive process. Okay, so I'm going to apply the Taylor expansion, and then after that, you might be doing an assignment for a higher order autoregressive processes. So again, you might need to address these coefficients. Okay, but that's not going to be the next assignment. That is going to be the assignment after that. Okay, so next assignment is just going to be simply based on this issue. Okay, so I'm giving you higher order autoregressive processes. Okay, and you would need to establish stationarity. That's it. Okay, so whether the processes are stationary or not. You would need to calculate some roots of quadratic equations, or that's solutions to quadratic equations. All right, guys, that's that. Okay, so that was it for today. You got questions maybe to your next assignment, which the deadline is on Friday. Don't forget that. Okay, if you might need assistance regarding matrix calculus, Some of you guys have already sent me some solutions. I haven't checked them. I need to evaluate also your third assignment, so that's going to be my task. But please don't forget your fourth. And your fifth assignment, again, I mentioned before, is going to be based on that. So if you see tomorrow's lecture, you know how to solve it actually. All right, guys? Okay, thank you very much and take care. Goodbye.